photon absorption and re-radiation in the atmosphere. This video is a supplement to the first video. We walk through photon absorption and re-radiation in the atmosphere with a little more detail than in the first video, but still under simplistic assumptions. I'm an engineer, not a climate scientist, physicist, or scientist at all. I could be mistaken about how things work. If you have a better, more physical understanding than this video, that's great. This lecture script is available as a PDF. The link is in the description of the video. Attributions for the images are given in the lecture script PDF. Let's start with this diagram. We are interested in the thermal emission from the surface of the Earth, its absorption by the atmosphere, and then thermal emission by the atmosphere. We want to see how the greenhouse effect returns some energy to Earth's surface, increasing its temperature. The magenta, blue, and green curves are thermal radiation energy spectra for thermal emission from Earth's surface at different temperatures. These are in the infrared range. Magenta is hotter temperature, green is colder. The blue area is thermal emission from Earth's surface that reaches outer space and escapes while the atmosphere absorbs or scatters some of the infrared radiation. So here, nothing has reached outer space because it has been absorbed by the atmosphere, and here, and here. But here, most of the emitted radiation from the Earth's surface makes it to outer space. The blue area is beneath the blue curve. Reduction of thermal emission from Earth's surface reaching outer space has heated the Earth. The gray area is the total absorption and scattering by the various molecules in the atmosphere between Earth's surface and outer space in either directions. Many wavelengths have 100% absorption or scattering between bottom and top of atmosphere. The atmosphere is opaque at those wavelengths. So here, 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 and so forth. This does not tell us the absorption length for a wavelength or whether there is 100% absorption from the middle of the atmosphere to the top or bottom. Note that the peaks of the magenta and blue curves, 9 to 11 microns, are within the partial transparency window here of the gray area. Absorption is not 100%, but not zero either. In that window, photons have a good probability of transiting the atmosphere. The cyan area is absorption and scattering by water vapor, the strongest greenhouse gas with the most impact on Earth's temperature. Notice the water vapor window of 7.5 to 20 microns, where water molecules in the atmosphere do not completely absorb radiation. They partially absorb it, but not completely. Note that the peak of thermal emission from the surface of the Earth is within this water vapor window at all surface temperatures. Notice that there is some amount of absorption or scattering at almost all wavelengths in the water vapor window. It is not completely transparent, and this will be important to us. The brown or mustard area is the absorption by carbon dioxide. Here, 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 here. There is a broad absorption band of 100% absorption centered around 15 microns within the water vapor window. This band produces greenhouse effect heating. Notice that the peak of the green curve is close to this carbon dioxide absorption band. Let's call the partial transmission wavelength window between 7.5 and 14 microns the water vapor carbon dioxide window for the purpose of this video only. It is not a standard term. Let's estimate an average of 20% absorption in this window. We will look at thermal radiation by the Earth's surface. We will ignore evaporation and condensation of water in this video, but it is very important for heat transfer and climate modeling. We will look at absorption by molecules in the clear atmosphere and completely ignore clouds. We will ignore convection in the troposphere. So, obviously, we're only looking at part of the whole picture in order to understand that part. We want to understand absorption and re-radiation qualitatively. I feel that some people will want some example numbers to help us understand, so I will do that, but we don't need accurate numbers to learn about radiation and absorption, and my numbers are not accurate. And remember, we're ignoring many other major aspects of atmospheric heat flow. Many processes occur simultaneously everywhere in the atmosphere. To help us understand the processes, I will break these up into a specific time sequence. But this is only to help us learn. Actually, everything happens everywhere all at once. Let's take a patch of Earth's surface at a single temperature, say plus 15 Celsius. The surface is nearly a black body with emissivity around 0.95. The surface emits black body spectrum infrared radiation upward into the atmosphere. Let's say that 15% of emitted thermal photons have wavelengths for which the atmosphere is largely transparent, and those photons will pass through the entire clear sky atmosphere and escape to outer space. And these will carry 30% of the thermal energy that Earth's surface radiates into the atmosphere. I show wavelengths for which the atmosphere is mostly transparent as blue arrows. The example numbers would be slightly higher for the hottest temperature on Earth. They would be much lower for the coldest temperature on Earth, because the peak wavelength moves close to the carbon dioxide 15 micron band. These percentage escape numbers are just for our discussion. Don't rely on them. So with 15% of emitted thermal photons escaping, then 85% of emitted thermal photons will be absorbed or scattered by molecules in the atmosphere. The atmosphere will be opaque. And these will carry, say, 70% of the radiated thermal energy from the ground. I show wavelengths for which the atmosphere is 100% absorbing from Earth's surface to the top of the atmosphere as brown arrows. Those infrared photons do not get absorbed by the nitrogen molecules, oxygen molecules, or argon atoms in the atmosphere. They are principally absorbed or scattered by water vapor molecules, but also by the other greenhouse gas molecules, carbon dioxide, ozone, methane, and nitrogen oxides. For simplicity, let's just describe absorption. Let's assume that scattering leads to absorption by another greenhouse gas molecule. Absorption of an infrared photon puts the molecule into a higher energy state of its complicated vibrational rotational states. It is not the case that the molecule is isolated and later emits a photon of the same wavelength as fluorescence. This does not occur because molecules are constantly colliding with other molecules 1 billion times per second. Infrared photons with thermal spectrum were emitted from the Earth's surface. Some photon wavelengths escaped to outer space. Other photon wavelengths got absorbed by greenhouse gas molecules in the atmosphere, at all altitudes in the atmosphere. Many or most of the absorbed photons got absorbed in the kilometer or even 100 meters closest to the surface, but some were absorbed at higher altitudes. Let's focus on an imagined volume of atmosphere close to the Earth's surface. That air volume initially had a thermal energy distribution at a temperature. If absorption could occur while other processes were halted, then absorbing some wavelengths but not others emitted from Earth's surface would give the air volume a non-thermal distribution. An internal vibrational rotational energy would be out of thermal equilibrium with kinetic energy of motion, translation. However, very frequent collisions of molecules exchanges energy and the volume rapidly thermalizes at a slightly higher temperature in this imagined step-by-step process. Translational kinetic energy gets thermalized, as do vibrational rotational energies. Thermalization includes the nitrogen and oxygen molecules, which are the vast majority of the collisions. Nitrogen and oxygen did not absorb infrared radiation, but their energies increased by the collisions with the greenhouse gas molecules, which had absorbed infrared radiation. So temporarily, the nitrogen and oxygen molecules, their kinetic energy of translation increased by colliding with the greenhouse gas molecules. As a result of the slight assumed increase in temperature, the air volume increases its thermal radiation. But how does that happen? Since the nitrogen and oxygen molecules do not absorb in the infrared, I believe they also do not emit in the infrared. But the greenhouse gas molecules do emit in the infrared. I believe that greenhouse gas molecules will emit at wavelengths that they absorb, and continued collisions and thermalization will transfer energy between all the molecules, including from nitrogen and oxygen, to the greenhouse gas molecules, where thermal infrared energy can be radiated. So there will be thermal emission by the atmosphere at wavelengths for which the atmosphere is 100% absorbing, and there will be thermal emission in the water vapor carbon dioxide window because the water molecules have some weak absorption at those wavelengths, and so they also have emission at those wavelengths. This is important. If this window were completely transparent with zero absorption, I believe it would also have zero emission. When water molecules in the atmosphere emit wavelengths in the water vapor carbon dioxide window, these emitted photons have a high probability of escaping the atmosphere, which is pretty transparent at those wavelengths, and a lower probability of being reabsorbed by the atmosphere. The radiation is isotropic in all directions. Let's assume that half the escaping photons reach the surface of the Earth, here, where they get absorbed by the surface, let's say, ignoring surface ice and snow, and half reach the top of the atmosphere and escape to outer space. Whether it's exactly half and half is not important to this video. The takeaway is that thermal emission by atmospheric water molecules in the water vapor carbon dioxide window returns some energy back to the surface of the Earth. This is the greenhouse effect, adding to Earth's heat. And some energy escapes to outer space. But some of that initial extra energy in that volume of atmosphere had initially been absorbed not by water molecules, but by carbon dioxide and methane in the atmosphere. Radiant energy from Earth's surface was absorbed by water vapor, carbon dioxide, and methane. Molecular energy got thermalized by collisions. Temperature of the atmosphere radiated infrared energy by water molecules, carbon dioxide, and methane. But the wavelengths in the water vapor carbon dioxide window, which then escaped in both directions, were emitted by water molecules, not carbon dioxide. When greenhouse gas molecules emit wavelengths for which the atmosphere is 100% absorbing, bottom to top, there are three cases. 1. Most of those emitted photons will get reabsorbed by the atmosphere, shown here. 2. A fraction of those photons emitted near the Earth's surface will reach the surface of the Earth without having been reabsorbed by the atmosphere, here. So it's a wavelength that the atmosphere can absorb, but these photons got through without being absorbed. 3. A fraction of those photons emitted high in the atmosphere will reach outer space and escape without having been absorbed by the atmosphere. When the infrared photons emitted by the atmosphere get absorbed by the atmosphere, the absorbing molecules will collide with other molecules, thermalization will occur, thermal emission will occur at all wavelengths, some wavelengths will escape the atmosphere to reach the surface of the Earth or escape to outer space, most photons get reabsorbed, and the cycle continues. More photons reach the surface of the Earth and outer space than if there were only a single imagined cycle. Well, that was the fictional version of a time sequence so we could understand. In reality, everything occurs everywhere all at once. There is no time sequence. Some percentage of the thermal radiation emitted by the Earth's surface that gets absorbed by greenhouse gases in the atmosphere gets returned to the surface of the Earth by the greenhouse effect, which increases the heating of Earth's surface. The process is complicated, and the net effect depends on the concentrations of different greenhouse gases, the temperature of Earth's surface and the lower atmosphere, and the density, pressure, and temperature profiles in the atmosphere. We ignored convection in the troposphere, we ignored evaporation, condensation, and clouds. So, repeating, don't rely on the example numbers in this video, but gain a qualitative understanding. I'm an engineer, not a climate scientist, physicist, or scientist at all. I could be mistaken about how things work, but I hope this video has been useful to you.